Okay, so for this graph here, 2 minus 2 cosine theta, we want to find the highest point on the curve. So we can kind of eyeball it up here somewhere, right? But what do we know mathematically about that point?
Can't you do like a tangent where dx equals 0?
Okay, dx equals 0. dy.
Or, yeah.
So dy d what? Okay, so there's really, we got two possibilities. dy d theta, and also dy what? dx. Does dy d theta equal 0 at that point, at that highest point? So what are we saying? For a small change in theta, for a very small change in theta, I want the change in y to be 0. Is that true for that highest point? If we think about a very small change in theta, so Andre says yes. So for a very small, for a very small change in theta, right through here, right through, it's like a little teeny change in theta. dy is 0. Yes? Yes? Yeah, sure. So for if theta changes a little bit, y doesn't change. Okay. What about dy dx equals 0? Is that true at that point?
Yeah. Oh, we need to turn the function into x.
Do we need to turn the function into y and x to answer this question if dy dx equals 0 there? Does it equal 0? dy dx? Well, what's the reasoning behind that? So how do we reason about dy dx? What are we saying? Allison's whispering. So what's the reasoning behind saying, yes, dy dx would be 0 or it wouldn't be 0?
Well, we would just look at a very small change in x.
Okay.
And see where y is up or down, I guess.
Yeah, so we've got a curve here, and we can think of it as a relationship of x and y. Now we're just saying for a very small change in x, is the change in y 0 on that curve? Sure, yeah. I mean, that's the same as your Calc 1 stuff, right? You got this curve. You know that at the peak or the maximum, when x changes a little bit, y doesn't change. So yeah, they're both of these derivatives are equal to 0. And both could be used to identify that point. So which one is going to be convenient for us? So what do we know? We know that r equals 2 minus 2 cosine theta. What does y equal? What does y always equal if you're talking about polar coordinates? R sine theta. It's bedrock. Always. If you're talking about the polar, you're putting the superimposing the polar plane on the xy plane, then y always equals r sine theta. So if we want to do dy d theta, all we need to know is what r is. What is r? What is it? 2 minus 2 cosine theta. And right, so we got y equals r, which is 2 minus 2 cosine theta times sine theta. So that's the relationship of y and theta for this curve. Right? Because if y is always r sine theta and r is always 2 minus 2 cosine theta for this blue curve, then that's always true on this blue curve, the relationship of theta and y. Does it make sense? R sine theta. And what did we want? We want to find dy d theta. So So we can work that out for this, or we can talk about what dy d theta is generically, right? If y is always r sine theta, and r is a function of theta, then how do we find dy d theta? If r is a function of theta times sine theta, then what will that derivative look like? Anybody? So generically, y is r is a function of theta times sine theta, right? So how will we do dy d theta if that's what y is?
Cosine theta r is
What's the general approach though? Product rule, right? Product rule. We got one function of theta times another. So what is dy d theta? It's going to be dr d theta times what? Derivative of the first times
sine theta
second plus
r times cosine theta.
first times the derivative of the second. See that? And so what would dx d theta be? Derivative of first times cosine theta plus first times negative sine theta. So I kind of stepped back from this particular problem, and we just derived what dy d theta and dx d theta would be in polar coordinates. Because if y is r sine theta and r is a function of theta, then it's a product rule, right? Do you follow where those come from? Y equals r sine theta. Product rule, you need product rule then. X equals r cosine theta. Here's the product rule on r cosine theta. Okay, so what about our particular example? We're going back to our example now, and we're interested in dy d theta, where it's equal to 0. So that we have this place where as theta changes a little bit, change in y is 0. That's going to give us our local max, local mins, right? In terms of max and min being the y coordinate. So we're going to use this one, and so we have what's dr d theta. So I'll come over here and I'll do it in blue. So for ours, dy d theta is going to equal dr d theta, or derivative of the first, which is 2 sine theta, times the second, times sine theta.
I have a question.
Please.
Why is it from dy d theta you have sines and y? Is it just because y is sine and x is cosine?
What is y equal to?
Okay, now I got it.
Yeah. Y is r sine theta, right? And x is r cosine theta. So I'm doing the product rule on r sine theta first for dy d theta, and then I'm doing the product rule on r cosine theta when I do dx d theta, right? All right, so we're doing dr d theta times sine theta plus r. What is r? 2 minus 2 cosine theta times. And we're interested in where that is equal to. Right there is where that thing's going to be equal to 0. Okay, so now we got some trig to do here. We got some algebra and trig to do. So I'm going to have 2 sine squared, and then I'm going to have 2 cosine theta and minus 2 cosine squared. So I first just multiply everything out. I multiplied things together and distributed the cosine theta to the 2 and the minus 2. So what we see here is we have a quadratic, because I have a cosine to the first and a cosine squared. So I could handle this and solve for theta if I had purely a quadratic in cosine. So how can I change this into cosines so that everything is in terms of cosine and I can form this quadratic of cosine thetas? So what would I do to the 2 sine squared?
1 minus cosine squared.
Yeah, so I can do 2 times 1 minus cosine squared. And that'll give me this quadratic of cosine, and hopefully it will factor. So it looks like in the end I ended up with negative 4 cosine squared plus 2 plus 2. This is pushing symbols, right? This is just arithmetic. Pretty easy so far. Let's divide by negative 2. So we get a positive out here in front because we got all 2's there. Since it's equal to 0, I can do that. I can divide by negative 2, and I get 2 cosine squared minus cosine theta minus 1. And now does that factor? Can I factor that into expressions here? So 2 cosine theta and cosine theta. So I need a product of negative 1 and a sum of negative 1. Does it work? Can I get it? So I need a plus 1 and a negative 1 so that the middle terms add up to negative cosine. This is going to be plus 1, and this one's going to be minus 1. So what I get? I got cosine theta equals, this one gives, this could be 0, right? So cosine theta could be negative 1/2, and then cosine theta could be 1. So where is cosine theta negative 1/2? Where is it? Where's cosine theta negative 1/2? Pi over 3. Anywhere else? Between 0 and 2 pi, is there anywhere else? No, this one. This isn't the only, right? There's a whole mess of angles that give you a cosine of negative 1/2. So any others between 0 and 2 pi?
Well, pi over 3 actually would be positive.
Pi over 3. What about?
No, cosine's negative x, right?
Oh, that's true.
So pi over 3 is here, and then in the third quadrant, what angle gives us the next cosine of negative 1/2? 4 pi over 3. And then from cosine theta equals 1, we get 0 and 2 pi. So if we're talking about just from 0 to 2 pi, all 4 of these angles, what? Give us a dy d theta of 0. So we'll go back to the picture in a second here and see why those make sense. But all four of these angles, for a small change in theta, the change in y is 0. Or horizontal, it heads horizontal for a second, right? Heading horizontal for just a moment.
Should there be 2 pi over 3?
Yeah,
What's that?
that would be negative.
Pi over 3
2 pi over 3
is
is
positive.
2 pi over 3 and pi over 3.
Thank you. You're right. Absolutely right. We're in the second quadrant, right? We're in the second quadrant, 2 pi over 3. Is 4 pi over 3 right? Is that one right? Yeah, because 2 pi over 3, 3 pi over 3 would be pi, and then 4 pi over 3. Okay, so these 4 angles, what? They're the angles that give us a dy d theta of 0. That's what we found out. Dy d theta of 0. So let's look. I'm going to erase everything and look at the graph here. Are we good with what I wrote on the screen? Okay, so now let's look at the whole graph. So let's start. So the first one was at 0. So at 0, do we see that dy d theta equals 0 when we first start out? Because it's like that curve, if we were to zoom in, it like the very first thing it does is it's just barely heading horizontal, and then so that's going to start curving up. But at 0 has a horizontal tangent, and then here we are at, there we go. Nope, that's not the right place. Back here. There we go. So there is precisely 2 pi over 3. And this is the point we wanted, right? So this is our, I mean, we said we wanted the maximum value of the curve. This was the point we wanted all along, and so it ends up being at 2 pi over 3. Next one was at what? 4 pi over 3. Does it make sense that dy d theta is 0 at 4 pi over 3? For small change in theta, change in y is 0. Last 2 pi coming in here when we hit 2 pi. So let's actually zoom in and see that this, because from that view, it doesn't really look like it, right? It kind of looks like it's coming in at a 45 or some kind of oblique angle, right? But if we zoom in, we should see that at 0, GC breaks down. Yeah, GC's having trouble. But we can see that it's kind of C, right? That it's not coming in at an angle. When you get to 0, it's going to actually flatten out and be horizontal. No, just the way that it graphs these, you can't really. Oh no, that's the way I've graphed it to make it thicker. So I've graphed several graphs so that when you look at it, that it's bolder. So that was me, not GC. So I graphed several graphs there. So it's correct. It's doing exactly what we told it to do. Because I wanted the curves to be bolder, so I made several graphs next to each other. Okay. Anyway, yes, it does come and get horizontal at 0 and 2 pi. All right, so we got that it was theta equals pi over 3. So what's r? So what is the r value? So the high point was right here. Theta equals 2 pi over 3. How do we find what's r? How do we get r? To get the coordinates of that point. Yeah, so this function is the relationship of r and theta. If I've got theta, it gives me the corresponding r. So this is 1/2. Oh, negative 1/2, right? Negative 1/2 gives -1. 2 minus -1 is positive 3. And that's exactly what it looks like. So we got the point 3. 2 pi over 3 is the maximum y value of the graph. Is the point of the maximum y value. How do we get the x and y? So if we want to get that in terms of x and y, what do we do? I want to get the x and y coordinates. R cosine theta, R sine theta, right? R cosine theta, R sine theta. It's -3/2. And then 3 square root of 3 over 2. So there's the x and y coordinates. -1.5, 3 square root of 3 over 2. Okay, how can I get the rightmost points of this curve? The rightmost points. Do you see where those are? What quadrants are those in? The rightmost points. And what quadrants are those in? First and fourth quadrants. We see there's these points of dx d theta. Another thing to talk about, instead of the rightmost points, we could talk about what? A vertical tangent, right? Saying the right and leftmost points of a curve and talking about where there's a vertical tangent are one and the same. See that? So that'd be here, be here, and it'd be here. So we would expect, so if we work through all the math of dx d theta equals 0, and we do all that stuff we did for the last one, we'd end up, we expect 3 values of theta, right? 3 values of theta, one in the first quadrant, one at pi, and one in the fourth quadrant. And those would identify our right and leftmost points, or where we have a vertical tangent. We won't do it. Questions on that? Okay, let's talk about, so how about down here at 5 pi over 4? I think that's right here. Is that right here? Or is this right here? 1, 2, 3, 4, 5. Something's missing here. I think it's here. Let's just do it. 5 pi over 4. Yeah, right here. So at 5 pi over 4, I want to find the equation of the tangent line at 5 pi over 4. How are we going to do it? What do we need to do that? See if I can sketch it here. Not bad. Worse. Theta equals 5 pi over 4. What do I need to get the equation of the tangent line at theta equals 5 pi over 4? What will I need? Okay, right. I'm going to need the point xy. And I'm going to need dy dx. Xy should be easy, right? R cosine theta, R sine theta, and how do we get R? The function tells us what R is for every value of theta, right? For every theta that we have, we get the value of R. So all that's left, so there's just a little plugging and chugging to do to get R cosine theta, R sine theta. That'll be the coordinates x and y of that point. Okay, what about dy dx? How are we going to get dy dx? Same way we did it with parametric functions. What do we do to get dy dx with parametric functions? So what are we going to divide, Allison? That's it? And dy d theta was r prime sine theta plus r cosine theta over r prime cosine theta minus. Is that what we found for those two? Make sure that's right. Right? Again, that's product rule on y equals r cosine, so r sine theta, and product rule on x equals r cosine theta, right? And what is r prime? So we're going to need r prime. What's that? So for this one, so it's this, right? So r prime theta is, or dr d theta? 2 sine theta. So this whole thing is going to be 2 sine squared theta plus 2 sine theta cosine theta. All over 2 sine theta cosine theta minus 2 sine squared.
It's not,
Something's wrong.
it's r equals to 2 minus 2 cosine theta. It's not r.
Right.
Y.
This is not right. Like this? Thank you. And what is our theta? Pi over 4. So just lots of arithmetic, right? Plug in 5 pi over 4 into this whole thing. And we're going to get a number, and that's going to be our slope, right? Once we plug 5 pi over 4, we're going to have our slope from our... We're not going to do this. You guys are looking glazed.
I have a question. So,
And from that, equation of the line. It would be kind of cool to do it just to get the line and then see that it has the right y-intercept and the slope is some shallow negative value, but it's not. That's not working all that. Yeah, question.
just to check, so if we want to get the points x and y, we first get r and then plug in theta and get the value that we get from
What are x and y in the polar
it's
plane?
r cosine of theta.
Uh-huh.
Sine cosine of
Good.
theta. Okay. So if we get an ugly number like square root of 2,
Well, they're going to be negative, first of all. X and y are both going to be negative. But yeah, they may be, yeah, they'll be in terms of square roots. Because 5 pi over 4, square root of 2 over 2, negative square root of 2 over 2, negative square root of 2 over 2. But we have to multiply each of those by r, right? So it's going to be a little more complicated than that. But yeah. See the roadmap to the end of this one? Can we see it and do it on our own time if we need to? So the last thing we got to talk about with polar coordinates for calculus is area. Let's talk about area. All right, so we got some generic function here like this. R is a function of theta. Okay, and so when we talked about area, like in rectangular coordinates, we started with a simplest case of from a starting value of x to a final value of x, right? From left to right, like x1 to x2. So what's going to be analogous in polar coordinates? From what to what? If before we did from x1 to x2, like left to right, what would be the analogous situation for sweeping out a region in polar coordinates? What's that?
it would be the opposite. It would be
Theta?
So it'd be first theta 1 to theta 2. Just like in parametric coordinates, it was t1 to t1, and then xy, x1 to x2. So it's going to be your independent variable, which in polar coordinates is theta. And so it's going to be from theta 1 to theta 2. And so we're interested in what is this area here. Okay? So before we do that, there's one kind of thing we had to brush up on a review here, is what is the length of a little arc length of a circle? So if a circle has radius of big R, and say we sweep an angle alpha in that circle, what, and radians, what is that length right there. We call it S. S, arc length equals, what is it? R times alpha, right? And you're using this, you use this in your Clara project, right? So that should have come up, you should have seen that came up in Clara. Arc length is angle measured in radians times the radius. So we're going to need that when we're going to do this here. Okay, so what is our typical element going to be? So we think about a little change in theta. So for a little change in theta in here, for typical element, we're always starting at the pole, right? So what's the shape of a typical element? It's kind of like a triangular sliver. Do you see that? Because it's always gonna come to a point at the pole. So it's not a rectangular strip anymore, but now it's like a triangular sliver. So our little bit of area is going to be based on the area of a triangle. So our little area is going to be 1/2 base times height. So we want to think of this side down here as the base. So if I could, so you can see this a little better, I'm going to kind of redraw this curve. That's a little easier to see. Okay. So what is the base? Or where is it going to come from? The base of this triangular sliver.
Delta, base, isn't base going to be delta theta, like a small change in theta?
But that's a length. It's not an angle. It's not an angle measure. It's a length, right? And so for the same change in theta, your length here is a lot shorter than your length out here, right? So you're in there, you got the right idea, but you can't measure a length with a change in angle. So it needs to be length.
So, is it delta?
This can be this thing right here, right? So it's a little bit of arc length, right? A little bit of arc length. And so what is our radius? Well, and the big R was just for the circle. So what is the, it's going to be R, right? It's going to be whatever R is for that particular sliver. That's going to change. As you do different slivers, you get different values of R, which is the distance out here. So the height is going to be R times, and what's alpha? D theta, delta theta. So that's our height. Oh no, that's the base. I don't know why I'm doing this. That's the base. It's the base of the triangle, sorry. It's going to be the distance out the R delta theta. And then what's the height of the triangle? So the height of the triangle would be from the base to the apex, this way. And what is that? Another R, right? So the base is this little bit of arc length right here. And that's the base of the triangle, which is R delta theta. And then the height of the triangle is R. It's from the base to the apex is also R. So we get what do we get? We get 1/2 R squared delta theta, and that comes from the area of a triangle. Get this thin triangular sliver. That's our element for polar area. Okay, and so then what's the total area? So now what do we want? You guys are all experts at this now. So total area is?
Go from 0 to 1 to 2.
Summing up all the typical elements. Start.
Can you just put R square
No.
or leave it like that?
That is R square. I'm not sure what you're saying.
Oh, okay, I didn't see that.
So we're going to sum up all the triangular slivers, and you got to think of them as sweeping out, right? Sweeping out from lowest value of theta, sweeping counterclockwise to highest value of theta. And we're going to sum up all those areas of those little sliver triangles. And that's what the integral does, right? Sums up all the areas of those triangular slivers. So do you have to, when you're doing the actual problems and you're trying to figure out how to set these integrals up, it's going to be really helpful to think in terms of this. Every sliver has its vertex at the pole. And those are going to sweep out counterclockwise through your region. And then the base of those slivers is following along your curve, right? The base of those slivers is tracing along the curve. All right, so let's go back to the quiz question. Let's do this one, and let's do an example here for this one. And that was 5 cosine theta minus 2. And so what I want to know, so remember how that traced out? We started at 3, and then down to 0, and then to negative 2, and then to negative 7 at pi. Then at 3 pi over 2, we were back at negative 2, and then we head back to 2 pi, we got to positive 3 again. So I want to find the area of the inner loop. I want to find the area of the inner loop. What am I going to need to do that? So
Is it 2 integrals by chance?
okay, so does it require 2 integrals to get the area of the inner loop?
It's just 1 multiplied by 2.
What do you want to multiply by 2, Andre?
The area of the half of the inner loop, the upper half of the inner loop.
So using symmetry, so could we get the upper half of the inner loop and then multiply it by 2? Yeah, make it as easy as you can on yourself, right? That's the easiest thing possible. So I think that's good. And that inner loop are in positive territory. It started off at positive 3, right? So what are we going to? So that's going to be our strategy. We're going to do the area of this first half of the inner loop and multiply by 2. So what are we going to need? So it's going to be 2 times an integral. But let's draw a typical strip here. So here's our typical strip. And we know that this formula 1/2 r squared d theta is going to sum up all those typical strips. So what's left? The bounce, right? So we got to get the bounce. How are we going to get the bounce? So from what angle to what angle are we going to sum up those slivers? 0 to pi over 2. Okay, so how do we all agree we're going to start our integration at 0? We agree with that? So we're going to start at 0. So the first sliver is like a horizontal sliver here. And then we're going to be summing up all these slivers to pi over 2. So when we get to pi over 2, where are we at? Yeah, so we're here. This is the point. Negative 2, comma pi over 2. So we need to figure out what angle. There's some angle. Remember we said there's some angle between 0 and pi over 2 where it crosses through 0. So we need to find out what that is. So there's some angle in here What's that?
You said it. You need r equals 0, so set 5 cosine theta minus 2 equal to 0.
Right. So here, we've got our equation. R is always 5 cosine theta minus 2. We're interested in what? What's true about this angle right here? The R value equals 0. We want to know where does R hit 0. So we're going to set that equal to 0. So it's going to be cosine theta of equals 2/5. So our cosine of 2/5. So at our cosine of 2/5, I'm going to write it this way for room's sake. 1/2. Okay, but this is in terms of theta. What is R?
5.
Right, so R is always 5 cosine theta minus 2 on this curve, so we can substitute that in, squared. So there's the setup. We'll talk through how we would solve this in a moment, but let's make sure we understand the setup. So what is this area of the inner loop? The total area of inner loop. Yeah, so use symmetry when you can, right? So use symmetry. We took that, we're doing the area of the top half. I'm just going to multiply by 2. Questions on the bounds or the setting up the integral? Are we good? So let's just talk about, so the 2 in this case and the 2 and the 1/2 go away, right? So the 2 and the 1/2 go away, and we're going to have the integral from 0 to arc cosine of 2/5 times 25 cosine squared minus 20 cosine theta plus 4. Okay? Very easy, right? How do we get 25 cosine squared theta? How do we do the antiderivative of that?
25 sine. No, it's
Remember that? How to do cosine squared or sine squared? What was it? Not change? No. You would need a sine, right? If it's cosine squared, it'd need to be times sine to do undoing the chain rule.
how we use the
Half angle identity, remember? Half angle identity. Remember that? That's how you do cosine squared or sine squared, with a half angle identity. But yeah, look for chain rule first. Always look in the trig integrals. You always look for undoing the chain rule first. But then you also know if it's just plain cosine squared or plain sine squared, just remembered that that's we do it with a half angle identity. Okay, questions on, again, I'm not going to finish this for time's sake.
What is the half angle identity again?
Cosine squared is 1/2
Oh,
1 plus cosine 2 theta. And if it's sine squared, it's a minus there. Is that right? Yeah, so it's just a, yeah.
that makes sense.
Okay, so then let's just talk about how we would structure these integrals to get other things with this curve. So that was the inner loop, 2 times the half of the inner loop. So what if we wanted the area of all this stuff? Just so here, the area within here. Think about how we would do this. So I'll make a red outline around it. I want everything inside the red cardioid, or cardioid-like shape. How would I get that?
We do the integral of the whole period and then deduct the area of the inside that we already got.
So you want to do the integral from what to what?
The whole period of the, so it would be from 0
0.
up to, I don't remember the period, what was the 7?
It was 2 pi. 2 pi gave us this whole curve. Yeah. So you want to go from 0 to 2 pi? Okay, and then what?
And then deduct the circle on the inside.
So deduct
So the area that
2 times 0 to our cosine, the 2/5. What do we think? Will it work?
Are we, when you ask for the whole cardioid,
Everything inside the red, what I drew in red.
okay, that'll just give us the big pedal.
What's that?
That integral will just give us the big pedal. It won't give us the cardioid.
Remember how this works. How does this integral, this formula, what does it generate for us? Triangular slivers to what? Always at the pole, right? So like once this goes, then what is it going to do? It's going to be calculating areas like this, right? Does it know that that loop is there when it's at these? Does it care about this loop right here? When it's going through all these angles theta and generating the areas of these slivers, does it know that this is here? Doesn't know. Okay?
Does the area overlapping, does it mean it's double? In that case, double?
Okay, when the angle is going, say, from this angle to, say, this was pi, right?
Yeah.
Pi -7.
Oh, so it would be just changing the bounds.
Okay, so when we go from that cosine, our cosine of 2/5 to pi, what's it going to give us? It's going to give us all this area here below the x-axis. It has no idea that this blue line is here. It's going to give us all the triangular slivers whose vertices are at the pole. And then when we go from pi to whatever angle this is, it's going to give us all that area up there.
So it would be just from our cosine of 2.
So the question is this right or not?
That's wrong.
What is that expression you used?
It's wrong.
Is this right or wrong?
It's right.
It's too complicated.
If we calculate from 0 to 2 pi, so there are two loop. We calculate 2 times of the loop area.
Right.
So
Right. So when we do from 0 to 2 pi, it's going to start by taking this half loop, right? And then it's going to give all this thing I've shaded down here at the bottom. Then it's going to give the whole thing shaded at the top. Then it's going to give, at the very end, it's going to give the bottom half of the loop. So when you do 0 to 2 pi, everything inside that loop gets counted twice, right? Because when you're out this outside part, it doesn't know the loop's there, and it counts all that area again as it's extending out to the larger curve, the further curve. So it does indeed, when you do 0 to 2 pi, it will give you everything in here, but then it's going to count that inner loop twice. So if you subtract that inner loop off once, it'll be right. Or we could do what?
From our cosine.
Right, we could do it from this starting angle. We could start the integral. Oh, I didn't want to do that. So whatever the starting, this arc cosine 2/5, the starting angle, and then end at, I don't know, whatever angle that is. 2 pi minus arc cosine 2/5. So we could start at arc cosine of 2/5 and end at 2 pi minus arc cosine of 2/5. And that would also give us all the area inside the red thing that I drew, because it would never find the area of the loop. And it would just get all that area. Well, the area of that loop would be included, right? It's included one time if you go from this bound to this bound. But that's two different ways to do it. Both ways are legitimate. Did I lose you? Ask me if I lost you.
Can we also do from arc sine 2/5? Well, 2 times the integral from arc sine 2/5 to pi.
Yes. Awesome. Yeah. So that what I shaded on the bottom, that's all that I shaded on the bottom is arc cosine 2/5 to pi. And she's saying now multiply that by 2. That's great too. Works great. And look, you don't have to worry about r's being negative and positive because what happens? In the integral, r is squared, so you don't have to worry about r losing area for negative r because in that area formula, there's no negative and positive r. Everything is just positive area, so that's nice. You don't have to worry about when r is negative, you're subtracting off your net area. So this is not net area. This will never be net area because it's r squared. Anytime r is negative, it's just like if it were positive. Okay. Okay, so one more example to do. Questions on that? Did you follow that? Okay. So here is, I've got two curves now. I got the original one, 5 cosine theta minus 2, and that's in, what, that's blue. And then cosine theta plus 1 is red. So here, so there's the top half of the inner loop for the blue one, right? So the one we've been working on, 5 cosine theta minus 2. And there's that angle where it goes through the pole, arc cosine of 2/5, right? And then, but I'm also sweeping out another curve here, g of theta cosine theta plus 1. How would we find the intersection of the two curves right here? How would we find that? What's equal? What quantity is equal?
Both equations.
Equations can't be equal
Oh, the theta.
when theta is equal. Is that right?
Yes,
And the
theta is
functions
equal.
have the same value.
But isn't theta always equal for both functions? I mean here, theta's 0.38, theta's 0.54, theta's 0.74, theta's 0.93. So what are we talking about to find that intersection point?
When the functions give the same value coordinates.
Right, and what's the values of the function?
Looks like
But what is that? What type of quantity do our functions give us? What do they give us?
point.
No, theta is the independent variable in a polar function. What does a polar function give us? R, right? R. So don't we want to know where R is the same, where the distance from the pole is the same? So here they're not the same. For G it's 2 and for F it's 3. But at this one single point, the R value is the same for both. So we're going to set R's equal, which means 5 cosine theta minus 2 equals cosine theta plus 1. So 4 cosine theta equals 3. Cosine theta equals 3/4. So that's why it's arc cosine of 3/4. Arc cosine of 3/4 is is the theta for the intersection point. And then the corresponding R value, the output of either of these functions, will be the R, how far away from the pole that point is. Okay, so if I look at this here, this was our half of the inner loop on the one we've been working on, right? This is the f of theta is 5 cosine theta minus 2. Right? And then this one is this is g of theta. It's the red one, cosine theta plus 1. So I've got three different regions there. I got the shark fin, right? Do you see the shark fin? And then I got this. What's that like? I don't know. And then this kind of triangular wedge over here. So how would I get these areas? So let's talk about the shark fin. If I bring the current angle back to there. So I want to get the area here. I want to get this area here.
The area of F minus the area of G.
He wants the area of F minus the area of G. Hunter likes it. Kaylee likes it. Right. So if you think about how the it works, right? If I did the area for F. So if I did the integral from 0 to our cosine of 3/4 of F, 1/2 r squared theta, what area would that be? What region would I get the area for?
From the pole.
All the way to the pole, right? All the way to, it would be this. That would be 1/2 r squared, where r equals f of theta. And so if I just want the shark fin, then what do I want to do? Subtract that. So the area of the shark fin is going to be so this is the shark fin, and this is all the blood, right? So I heard a quote. Whenever you think your idea is stupid, just remember that a group of people sat in a room and had the idea to make a movie of a tornado of sharks, right? Okay. So something like that. All right. So area of shark fin is going to be the area from 0 to our cosine 3/4 of what? 1/2. What is r for this one? 5 cosine theta minus 2. Okay. Minus, same bounds. Three-fourths. That should be a 4. 1/2. What's r? Cosine theta plus 1 squared. All right, so that's a shark fin. Does the shark fin make sense? Yeah, so it's going to be, we need all the area out to the F curve minus all the area out to the G curve. Okay, so that's that area. So now what about this area? So now this one. But I gotta make sure we know what we're looking at. So I'll draw a black dotted line around it. This. I want this area here.
It should have to be 2 integrals.
So do you see the reason I'm talking about? I put a black dotted line around it. I want to get that area. How am I going to get that area?
It's 2 integrals. Like,
What am I going to do with the 2 integrals?
you're gonna add them.
She wants to add 2 integrals. Joseph thinks that's right. Can I do it in 1 integral? So let me give you a visual here. So what was the red curve? Was that the cosine plus 1? So we're really going to start with cosine plus 1 as we go from 0 to what? arc cosine of 3/4, right? So that will be part of it. But then when we hit arc cosine of 3/4, then what?
It's going to be the integral of 5 cosine.
It's going to be the other the 5 cosine minus 2, right? So now theta is going from arc cosine of 3/4 to arc cosine of 2/5. So in this case, we're going to add integrals using the different functions, right? We're going to always think sweeping counterclockwise. So we're going to sweep to the red curve, and then when we get to the arc cosine of 3/4, we're sweeping on the blue curve. So you guys set up the expression that will get that total area. Go. Oh, I'll write them down again. So the blue one was the one we've been working on. That's f of theta. And the red one is there. So it's going to be an integral from 0 to arc cosine of 3/4, 1/2 plus integral from arc cosine 3/4 to
Because arc cosine is
5ths of the blue one. So when you have these kind of tricky areas that are based on two different polar curves, the key is you got to remember you're always sweeping counterclockwise, and your slivers always reach to the pole. Every sliver reaches to the pole as a vertex, like triangles, right? You think of triangles being swept out counterclockwise. Every single one of those is going to reach to the pole, and that will help you make sense of when do I subtract, when do I add, okay? Okay, finished on the dot. So that was the last example. So the exam. So the exam is tomorrow. I'm sorry that you don't have a couple days to study for it. You should have a couple days to study for it, but summer school course just can't happen. So I posted the. Let me show you that stuff. For if you go to exam prep and homework solutions. List of topics and book review problems, that's comprehensive in terms of the topics. So I've narrowed it down. Like you don't have any of the lead up to Taylor and Maclaurin. The only thing about series and sequences is Taylor and Maclaurin series, nothing else. Just what was not covered on exam 2. All right, this is a big chunk. Maybe parametric and polar, maybe 1/3 to half of the exam, okay? And then the other half, or 2/3, physics applications, areas and volumes, integration techniques. But parametric and polar stuff is weighted more heavily because we didn't have an hour exam on it. Okay, so that's all those problems are really helpful to get ready. And then on the other thing that you already saw from your homework today, everything on this is good practice except just ignore this page. Functions of series. Like I said, the only thing that's on the exam that's series is Taylor and Maclaurin series. So we already had our exam on this. We don't have to do that again. So this page is fair game. Parametric function, that's more good practice. And then all this polar graphing. So there will be a no calculator portion where I'm going to ask you to sketch polar graph, okay?
For the calculator portion, can we use a graphing calculator, or do you want the non-programmable?
I think graphing is okay. I have to. I'll have to confirm that with you by email, but I'm pretty sure I said graphic calculator was okay for this final. I have to look it over. But yeah, so there's going to be multiple choice. There will be a free response, just like the other exams. We'll meet here same time tomorrow.
Do we have web homework?
Yeah.